Good morning, everyone. Thanks for tuning in to the third quantum computing weekly recap video. This week we have a lot of news coming out of China, some software updates, and some computer sales. So let's jump right into it. First off, big news coming out of China. They've announced the launch of the Tianyan 504, which is a 504 qubit superconducting quantum computer, which is an incredible number of qubits. And apparently they'll be available to use on the cloud platform, China's telecom quantum computing cloud platform. This is really insane news. I don't think anyone's seen this number of qubits from a superconducting qubit gate-based operations. Really easy to use. Companies like D-Wave have thousands of qubits, but those are quantum annealers, so they solve a different class of problems. These sorts of computers like the Tianyan are general computation devices. So you can do anything you do on a classical computer, you could theoretically do it on a quantum computer, but you probably wouldn't want to do those things. So very exciting news. I am really wanting to try to find out how to access this cloud platform. We'll see if I can. Not sure, but exciting news from China. And China also announced that with the team from China and US, they were able to create a very stable time crystal. And what this is it's a structure that you can create with qubits that over time, the energy of the system will be oscillating between two different states, which is very exciting and sort of mind-bending. It's almost like a Newton cradle, maybe, that just never stops. Just something that goes back and forth, never stopping, like a little metronome. And what this could be helpful for is if you can somehow encode your quantum circuit into the time crystal, where your states of oscillation are kind of the states you're wanting it to be in, then you can have very long, resilient quantum circuits where if errors propagate over time, you won't have those errors at all. So it's very exciting, kind of mind-bending, but this is a great step forward. It's really cool to see China making so much progress in a week. Oh my gosh. If you couple this 504 qubit machine with time crystals and somehow encode a quantum circuit into that, I think you can have, very useful quantum algorithms pretty soon. So that's exciting. Another big news, kind of incredible, the IonQ stock went up 142.8% from November, which is just crazy. If there's consistent revenue growth, and I guess the market's reacting to that, some cool, developments, some cool news updates, working with NVIDIA. They're provided on all the cloud platforms. It's really impressive to see this. I guess, that's a little stock update for this week. Then we have Pasqal, and they sold one of their 100 qubit devices, and Pasqal's a neutral atom quantum computing company. So very similar to trapped ions like IonQ, but some people even say that the neutral atoms are a better way of doing computation. Maybe they're better in some ways, maybe they're slower, I'm not sure. But getting to see a company with 100 qubits, with the fidelity and the T1, T2 times, the decoherence times of those qubits being so high, it's really exciting. And I think it's great that we have governments buying non-superconducting qubits. For a long time, it was just IBM selling to all these different countries, which is fantastic, but we're seeing smaller companies like Pasqal who are selling, an amazing machine, and the whole idea is that it's going to be coupled with their supercomputer. And this is a step that a lot of companies are taking right now, where you have certain quantum speedups. Like for Pasqal, that would be, Hamiltonian evolution. So if you have a algorithm that can be encoded as a matrix, that define that problem, and you can evolve it and find the minimum energy of that state, you find the solution. And quantum computers are really good at that. So it could be the case that we have very complicated problems with Germany's supercomputer, and Germany's supercomputer can format these problems, like, weather problems or something, into a Hamiltonian that is good for Pascal's computer to solve. So this hybrid computing is getting really popular in recent years. So, or like the recent year. So we'll see how this looks, and I would assume if they're successful and they have some, great deliveries on different problems, great solutions, we'll see more and more funding from other companies and more purchases, especially more integrations with their supercomputers. Then we have some investment from Multiverse Computing. They're a popular software company. They don't build quantum computers, but they make a lot of cool AI software, and they're even on the Qiskit functions catalog, the new Qiskit functions. So they're definitely doing great work out there. They're at the cutting edge. They just got funding, which is exciting. There's not enough, I think, software companies in quantum. There's a lot of hardware companies. So we definitely need the user experience to be better, developer experience to be better. And these software companies, because they just focus on the software, they're going to do a great job of getting, I think, more and more people in. So this investment makes a lot of sense. Diving deeper into software, we have Qiskit version 1.3. We're marching toward version 2, and this version has a lot of great updates and something that I'm a little disappointed about. Overall, in version 1.3, we have about 6% improvement across transpilation delivery. Yeah, so 6 times, oh, did I say 6%? Sorry, 6 times, 600% speed up for transpiling. And what they did is they rewrote, I think, most of Qiskit's backend in Rust, which is a low-level language that's very memory safe. So we're not going to have a lot of, wasted time on, garbage collection, things like that. But it'll still be safe. So 6 times speed up is incredible. They're also improving the way, gates are used when you're doing quantum volume or any normal circuit to something like a Hamiltonian evolution, like I talked about before, or chemistry simulation, that are defined by polyevolution gates or polyexponential. So that's exciting. But the sad part, in my opinion, is IBM is deprecating pulse level control. Their open pulse, no, it's Qiskit pulse, I think. Yeah, I worked on this when I was, a couple years ago, and I thought it was a very cool feature. You could define your own microwave pulses and create anything you wanted. You could apply that to qubits. You can even excite them into a state called qtrits, and I think it's a disappointment that they're deprecating it, but I hope that some other hardware companies provide this feature. And then again, if it is even being used, I don't even know if people use this, so I never use it, but it still was a cool feature. Maybe it is the good move to get rid of it. And for our final news story, we have some cool Python library coming out of the Max Planck Institute, along with some other people who created a Python library called PyTheus. PyTheus is pretty interesting because it almost takes ZX calculus to another level. Let me show you what I mean. So we can represent a quantum circuit as a graph, and Qiskit does that with their network X that they rewrote in Rust, which is incredible. And there's also some ZX calculus specific quantum circuit optimizers. But this paper kind of proposes, hey, what if we took most of the entire stack and represented it as a graph? And we can even include like the amplitude, which is common, but correlated photon pairs, single photon path, things like we add in this paper. They added so many different edges and information between different types of objects in the graph. So incoming photons could have a negative amplitude. You could encode that. With ZX calculus, really you're just encoding the quantum state between qubits. And what they're able to do is take a much higher complexity and represent more of the problem as a graph, do stronger optimizations, and probably getting way higher performance out of their optimizer than maybe the ZX calculus method would. So I'm excited to see if this kind of structure could be used on the back end in popular, simulators like Qiskit simulator, their air simulator. If they represent more options for the users, like where the qubit's being measured, how that measurement happens, all of that, and maybe integrate it with Qiskit Metal, I think this kind of work here can have a big impact on how our simulators most efficiently optimizing quantum circuits. Thank you very much for tuning in. I hope you enjoyed the third weekly quantum news recap. If you did, please like and subscribe. If you didn't, hit that dislike and let me know what I can improve for next week. Have a great week, you guys.